In our next sequence, we are going to revisit the small signal trick in the context of amplifiers. The reading will be the chapter 8 of your textbook. Let's start with a quick review. We've talked about the MOSFET amplifier, which was built with our little MOSFET. It had its gate, drain, and source connected in this pattern. So as I've been saying all along, in 6002X, we will see a lot of patterns. Patterns are stylized ways of building circuits that we will repeat over and over again. This particular connection of the MOSFET is one example of a pattern. We will see other patterns. We've seen the voltage divider pattern, where we had a series pair of resistors connected to a voltage source, and we took the voltage from between the two resistors. That was a resistive divider. We also looked at current dividers that worked like this, where I try to divide up my current in some ratio. So these were just some examples of patterns. Another really key pattern that we saw was the Thevenin pattern, where I replaced a bunch of circuitry with this pattern, and then I connected some device D, that was the interesting device, to my Thevenin pattern. So voltage source in series with a resistor, which in turn was in series with a device of interest, is another pattern. A complementary pattern, which is the dual of the pattern above, is a current source pattern, a Norton pattern with a current source and a resistor, and we connected that to some device D of interest. This is another very common pattern. Okay, with that little quick tour of patterns, let's get back to our MOSFET amplifier. And we said to make it work reasonably well with some amplification, we are going to follow the saturation discipline. Now, there's really no reason for us to do this. I mean, we could have picked any other way of using the amplifier, but we said if we operate the amplifier in the saturation region, I'm going to get good amplification. And so we said, let's just stick to this region for the MOSFET operation. Now, in designing circuits with MOSFETs in saturation, we first had to make sure that the voltages that we applied were such that the MOSFET stayed in saturation. Okay, so in order to do that, we defined something called large signal analysis, and this had two steps. The first step was to go and find the transfer function under the saturation discipline, V naught versus I for the amplifier above. And the second step was to find the range of input values Vi under the saturation discipline, okay, and the corresponding ranges for V naught. And by operating the amplifier for the given values of Vs, RL, and the MOSFET parameters. And what are the MOSFET parameters? Are K and Vt. And based on those two parameters, we know that IDS for the MOSFET is given by K by 2, Vi minus, or I should say VGS minus Vt whole squared. So K and Vt are my MOSFET parameters. So for the given MOSFET parameters and for RL and Vs given, I could find a set of ranges for my input voltage Vi and a corresponding set of ranges for V naught, and also a corresponding set of ranges for IDS. And as long as I operated within those ranges, my circuit would stay in the saturation region. So that was pretty interesting. Let me very quickly continue the review of large signal analysis and look at steps 1 and 2 in a little more detail. So the first step, as we saw, was to figure out V naught versus Vi for the amplifier. Let me just draw that here quickly for your reference. So this is Vi, this is V naught, RL, Vs. And so we did the analysis of V naught versus Vi, and we found that V naught was given by the expression Vs minus K times Vi minus Vt whole squared times RL, and that divided by 2. So that was V naught versus Vi for the amplifier. And then we said, let's go and figure out the valid operating ranges. And let me quickly summarize what we saw here. So what I'm showing you here is the MOSFET transfer curve, V naught versus Vi. And notice that the equation here applies only to this region of MOSFET operation. Okay, so let me just mark out that region. This is the saturation region of operation for the MOSFET. At the upper end, the MOSFET exits saturation when VGS, or Vi in this case, is less than Vt. And similarly, it exits saturation where VGS is such that VO is no longer greater than Vi minus Vt. In fact, when VO less than Vi minus Vt, the MOSFET goes into its triode region, and we're no longer in saturation, and so we have to maintain the constraint V naught greater than Vi minus Vt. So we looked at finding the valid operating ranges for the MOSFET, and we did so. And what we found was that the interesting region of operation, the saturation region, was given by this range here. Okay, this is the interesting range for Vi where the saturation discipline was satisfied. So as a typical example, if I had a MOSFET with Vt of 1 volt, it's not unusual to find that the valid range of operation is on the order of say 2 volts. And for the demos done in class, we picked Vs to be 5 volts. And the low voltage in this case for the output would be 1 volt. And why is that? Well, if my input is 2 volts here, then if this is 2 volts, then notice that for saturation operation, this value here needs to be greater than 2 volts minus Vt. Okay, it needs to be greater than or equal to 2 volts minus Vt. In other words, greater than or equal to 2 volts minus 1 volt in our example, or greater than or equal to 1 volt. Okay, so therefore, this is how I got the 1 volt here. So for a Vi of 1 volt, my output V naught can go no lower than 1 volt and still satisfy the saturation discipline. So this was the interesting region for Vi. Then the corresponding region of interest for saturation region operation was given by this region here.